Hello, today we'll be looking at using Python and statics. We'll be using a simple equilibrium of a particle with three forces acting on it. And I'll show it with geogebra.org to show the geometry of the problem. And then we'll be using Python in the form of the Spider IDE, Integrated Development Environment. We'll use the law of sines, and then we'll look at components. And when we do components, we'll do that two different ways. We'll do it symbolic, and we'll use linear algebra. This is the problem. Essentially, in a ship unloading operation, we're unloading a 3,500-pound automobile by a cable. And a worker ties a rope to the cable at A and pulls it in order to center the automobile where he wants it to land. At the moment pictured in the picture, the automobile is not moving, the ring is not moving, and neither is B. And the angles between the vertical and horizontal are given there as 2 degrees and 30 degrees. So what do we know? Looking at this problem, well, we know the weight of the automobile is 3,500 pounds. We'll call that W. Say W equals 3,500 pounds. We know the angle of the cable. Again, the cable is running vertically or near vertical, and it's 2 degrees. So we'll call that angle B because it's at B, and we'll say that's 2 degrees. We'll look at the angle of the rope below horizontal, and that's 30 degrees. So that's what we know from what's given. The main thing when doing a word problem such as this is, what is the question? So we look up here and reread our problem statement, and we see that it's looking for the tension in the rope. And we'll name that, again, T sub AC for tension and between A and C. And it also says it's the tension in the rope and the cable. So we need to also find the tension in the cable, and we'll call that TAB. Summarize our known information in a table here is a nice thing to do. Now we'll look at this problem, and it's a statics problem. It's not moving. So in statics, the first thing we almost always do is a free body diagram. We try to draw the forces acting on the particle. The particle A has 3 forces acting on it. Again, it's got the tension of the cable up at 2 degrees, and the tension at the rope down at 30 degrees, and the weight acting straight down. We could also include the names over here in our free body diagram. Since we know that information of 2 degrees, 30 degrees, and 3,500 pounds. For the first task, what we'll do is sum of the forces equals 0. And if you remember to some vectors, you can place them tip to tail. That is, you take the starting point of TAC and move it down to the tip of the weight, and then take the starting point of TAB and move it down to the tip of TAC. When we've done that, this is what we end up with. Again, we don't know the length of TAC or TAB at this point. So let's go on and see if we can find that length. I'll be using GeoGebra to work this, and we'll start with this forced triangle drawing. So GeoGebra here. First thing I want to do is put a point at 0. I always like to call that O equals 0, 0. So I put a point there. And I need to add a point for the weight, because we'll know where the end of the weight is. So I'll add a point at 0. The x value is 0 because it's straight down, and minus 3,500. And GeoGebra automatically gave it a name of A. So that's our weight vector. Now we want our tension in our rope vector. To do that, it wants to be 30 degrees down to the right of A. So I want to put a horizontal line in, and a horizontal line is just y equals minus 3,500 in this case. And then I'll use this rotate tool, and I'll rotate this line. So I'll select the line, and then I'll select the point I want to rotate it about, which is A. And I want to go clockwise 30 degrees. So I hit OK, and I get a new line that's been rotated 30 degrees. I can hide the original line, is OK. Likewise, I want a vertical line, which is just x equals 0. And I want to rotate that line also. So I click the line and the point I want to rotate it about. Now, in this case, I want to rotate it counterclockwise by 2 degrees. Again, above the O is going to the left, so that's counterclockwise. Again, I don't need that original O value. Again, the main point I'm wanting to find is this circled point here where these two lines cross. And to do that, I use the intersect tool. So I'll just intersect these two lines, and that will give me this point where they cross. Now I'll add some vectors. We can hide these lines. We don't really need them anymore. And we'll do a vector from O to A. And we'll rename that one just to be consistent. We'll call that W, because that's our weight vector. And I'm going to move the W over to the other side just to make space later. Now I'll add the vector from A to B. Again, I'll rename that T underbar close AC. The braces make both those the underscore. So we can see TAC, and I'll move it down here where we can see it better. And our final third vector will go from B back to, let's see, let's start over. Vector from B to O. And that was named U automatically, but we want to rename that again, T underscore A B. So we hit OK and move that out. Now we don't really want we've got the components of these vectors, but what we really want is the magnitude. And a quick way to get the magnitude in this case is to draw a polygon, because GeoGebra will give me the length of each side of the polygon. So I get A is equal to this TAB. W is equal to B, and TAC is equal to O. So those are my answers. Again, A 3574, the weight is 3500, which is what we were given, and our force off to the side is 144 pounds. Okay. We can keep this triangle up here and use the law of sines. Remember the law of sines. You probably learned it as A over sine A, B over sine B equals C over sine C. So to use the law of the sines, what we really need to do is need to know a side angle pair. And if we look at our triangle, we see we know W, we know the weight is 3,500 pounds. And we also know the angle here is 58 degrees. We got that 58 degrees by subtracting from 180, since the sum of these three angles is 180 degrees. And it was 90 plus 30 for how far we were going down, and then the 2 degrees at the top. So we know those two things. I like to rewrite the law of sines here, so there's a pair that we know. So we know the side and the pair angle, and that equals the unknown side divided by sine of the angle opposite the unknown side. Or rearranging this, we have the unknown side equals a pair side times sine opposite angle over pair angle. Now I'll write this off to the side here, because that's the equation I'm going to use to solve my problem. So let's look at this problem with the spider. I am only going to use the console in this case. And what I need to do before using math functions in Python is to import it. I'm using the Python in a vanilla version, so I still have to do this action. You can set up Spider to do these things automatically. So I'm going to import everything from math. That gives me, as you can see, some variables, e, pi, and tau, as well as sine, cosine functions. So then I want to set W equals to 3,500, and I may put a comment there. I like to put this is the weight of the auto, and that's in pounds. So we see that our W appears on our list of variables now. And I want to do these angles, set these angles, and Python uses radians for the trig functions. So I'm going to call it angle AC for the angle opposite AC, and say that equals radians of 2. So that will be angle AC. And I also want angle AB, and that'll again be radians 120 degrees. So we've got the one more angle we need, angle W, the angle opposite the weight, is equal to radians again of 58. So now I've got all my angles in radians, and I just want to go down here to my equation and say the unknown side, let's say T sub AC equals W is my pair side times sine of angle AC divided by sine of angle W. Again, that's the pair side, so W over angle W. And we can see the value at the top is TAC. If we wanted to see the value in the console window, we just enter TAC and get that value. Or another way to do it, we'll do with TAB equals W times sine angle AB divided by sine angle W. And then I'll hit a semicolon, and that allows me to enter another instruction line on the same physical line, and I'll just do TAB alone. So it prints out TAB. So TAB is 3574 and TAC is 144. Okay. We'll clear those and go on to the next method. We can do our sum of our forces as components. So we can have, again, sum of the forces in X equals 0 and sum of the forces in Y equals 0. Now, to start with here, I'm going to use standard X and Y directions. We get to pick these directions, but we'll just pick them as standard. So let's write sum of forces in X is 0. So we have TAB. Its component would be at the top here. It's negative, and it's sine of 2 degrees times TAB. TAC would be along, again, the x-axis here, and it's cosine. Cosine because the angle is in contact with the hypotenuse and the side of 30 degrees. Likewise, sum of the forces in Y equals 0. That gives me, again, Y is up, so TAB times cosine of 2 degrees would be the force up from TAB. TAC times sine of 30 would be the force down, so it's negative, and our weight's acting down, so we make that negative also. Now I'll save those equations since that's what we're going to solve. Again, we have two unknowns, TAB and TAC, and we have two equations. So we'll work the symbolic solution. To do the symbolic solution, I'm going to again import all the math functions. I'm also going to import the symbolic package, which is called sympy. And I'm going to name it something a little bit easier to type. sim. So every time I'm using a symbolic function, it will start with SYM and a dot. We want W still as 3500. I won't put the comments in this time to save time. Now we need to define the variables as symbolic. So I'll do that. One of them, TAB, comma, TAC equals, again, sim dot means it's from the symbolic package, and I'll define it here as symbols. And what symbols I'm going to use, of course, is TAB, a space, and TAC. And close. There is a capability that you'd want to maybe call symbols by a different name than you define them, but that's fairly rare. Okay, now let's put the fx, and I'm going to set that equal, but what I'm going to set it equal to is an equation. So it's not a variable, but an equation, which is EQ. And then I'll enter the equation, TAB times sine. And again, I want to make sure it's in radians of 2 degrees plus TAC times cosine radians 30 . That's on the left side, and on the right side I just have 0. So I've defined my sum of the forces in X. Now the sum of forces in Y will be done very similar dot EQ TAB times cosine radians 2 minus TAC times sine, and radians 30. And the last thing we have here is our minus W on the left side of the equation, and we'll still have 0 on the right side. Now the magic command for solving things symbolically is sim.solve. And we can get our help directions if you just type Control-I. It will bring up the description of the command you're trying to use. Again, it's quite powerful command. Solve. So we want to give it our list of equations. A list in Python is a square bracket. And we just want fx and fy, our 2 equations. Now we give it another list of the variables we want to solve for. So we want to solve for TAB and TAC. And that's all you need to do. And we have sol. And if we just enter sol, again, we can see the results. TAB is 3574 and TAC is 144. But sometimes we want to set different variables to use later from our solutions, because TAB and TAC are still symbolic even though they have a numeric value. So I can set TAB equal to sol, and I'll just use the name of the variable TAB as such. Now this TAB is still a symbol, but it's just isolated from the solution. But if I want to change it actually into a number or a floating point number, I'll do that to TAC. But I could also print it out. For Python, you use the print command. We'll print things out. A quote, let's say TAB equals, so it'll print the text there. Now I want the first variable in the list, which starts at 0. Python starts at 0. And I want to print it out with a 0.4G format. What that does is have 4 places of precision from the 0.4, and G is general, which tries to write it compactly. Now we can actually put our units on here to print it, and we'll print TAC in the same manner, but it'll be number 1 variable, 0.4G, close, pounds, and I'll add a blank line just as a \n, and end the quote. That makes a string. Now to add the variables, I use a format command, and again I put my TAB and my TAC in here. So again, the TAB is symbolic, but it will get converted to numeric here, and the TAC is already a floating point number. We can even see it up here on our list of symbols. So when I hit enter here, it should print out the results. TAB is 3574, TAC is 144. Okay, we've got that one. Let's look at another method for solving this problem. We'll go back up to our 2 equations and 2 unknowns. But we want to rewrite it. We want to rewrite this in standard form. And in standard form, we write it as a number, a known value that is, times our first unknown, plus or minus a number times our second unknown, and so on, and then equals everything else goes on the right. So the second line, again, this minus W went over to the right side, and we have TAB and TAC lined up above each other, or above themselves. So let's take a look at how this gets manipulated into a matrix. So the first thing we can do is move the TAB and TAC up to the top and squeeze things together so the numbers multiplying TAC are under it and the numbers multiplying TAB are under it. Then we'll group the numbers into a matrix that has 2 rows and 2 columns. Then we'll make some room over here and move our TAC and TAB down with TAC on the bottom. And we'll put those in a group, a matrix. And while we're at it, we might as well put the right side in a group. Note that the TAB coefficients are in the first row, and the second variable's coefficients are in the second column, TAB is the first column, TAC is the second column from our original equations. When we summarize this as A times X equals B, make it as simple as we can, but we need to look at A is this first group as the numbers, X is our unknowns, our variables, and B is the values on the right side as a column. Column is up and down, and a row is side to side. And to solve this, you might think you'd solve, if this was just a simple algebraic equation, you just divide both sides by A. Well, that's what you do in MATLAB, but there's a special divide operation here that's A backslash B. So it's really dividing it on the left side, which is what you have to do for a matrix solution. So we'll write our A, X, and B, and we'll bring Spider back and clear it out. So we get a new kernel, and we'll still import our from math, import everything. And the package that does linear algebra and much other things, very similar to MATLAB, is numpy. And I'm going to give it a shorter name of NP, again, just so that I can type it smaller. So I want my matrix. So I want A, and it's going to be an array or a matrix. And in Python, the whole matrix will be a list element, which again is a square bracket. And then the first row will also be a square bracket. And we want minus, again, sign radians of 2 for the first element, and cosine radians 30 for the second element in the row. And we'll end that row with a square bracket and put a comma, and we'll put another row in. Again, cosine radians 2 and minus sine radians 30. And we need to end both those. I must not have ended enough. Sine. Oh, I didn't end the array. Now we have an array up in our variables. It's a 2 by 2 array. If we want to look at it, again, we just hit A. And we see again that it's all numbers. It is an array here, and it's all numbers. Now if I'm using arrays and the solve, I don't need to make B a column vector, I can make it a row list, and it'll just have 0 and W. Yep, I must not have defined W yet. 3,500. So B equals 0 W. Okay, to solve this now, we'll get a solution, and equals, and again it's something from NPy, and it's actually a sub-package inside NPy, which was called linear algebra. Linear algebra, which is linalg. And in that package, I'm going to use its solve function, which is A, comma B. And I'll use a semicolon and put sol out here so we can see what the answer looks like. Again, the answer is an array. The first value is TAB, and the second value is TAC. So we want to extract those. TAB equals sol. And again, in Python, the arrays start at 0. And I'll just put TAB out again just to show that TAB is there. And TAC equals, again, the solution, the second element. And I'll write TAC out again. I could do a print statement here, but I'll skip that for now. But we got the same values that we got before. So in our Python and statistics, we're looking at equilibrium of a particle with 3 forces. I did GeoGebra.org and got our solutions for TAB and TAC. And in Python, I used law of sines, got the same values again. And we looked at components. When we did components, we had 2 equations and 2 unknowns. So I did a linear algebra solution and a symbolic solution, and got the same numbers that we had before. There's still another way to do it. One more way, looking at it, let's look at our free body diagram. And if we, instead of making x horizontal and vertical, we can align the x-axis with TAC and the y-axis perpendicular to that. When we do that, we'll notice the angle between our weight and our x-axis is 60 degrees. And the angle between our y-axis and TAB is 32 degrees. So we can do some of our forces in y now. Again, this is a different y. We see we've got TAB times cosine of 32 in the y direction. And we'll have a component then of the weight going in the negative y direction, and it's the opposite side of the 60 degrees, so it's sine 60 degrees. Now here we only have one unknown, TAB. So we can actually solve for TAB. It's W sine 60 divided by a cosine of 32. Now we can do some of the forces in our our new x direction. And we see TAB times sine 32 going in the negative x direction. Our W times cosine of 60 in the positive x direction. And our TAC is moving all the way in the x direction. So it's here. Again, we know TAB from this first equation, so we can then solve for TAC. So we have now two equations to solve. Write them again over here. Bring Spider back. Again, from Math, import star. Import everything. So we just want TAB. Let's define W. W equals 3,500. And TAB equals W times sine. We still need our radians. 60 divided by cosine radians 32. And our TAC equals, again, now we know what TAB is. It's just a number, times sine radians 32 minus W times cosine radians of 60. So we can again look at TAB and TAC and see that we, whoops, TAB, oh, I did 6 degrees instead of 60 degrees. So let's go up. I use the up arrow key to go back in previous commands. And I'll change that to 60. I'll check TAC again. And we got our 144 again. Okay, one more thing we could do. We'll do with this one. Just to show you don't really need the things, we could actually use a spreadsheet. So I'm going to say W is 3,500 pounds. Then TAB, and that will be W, but instead of W, oh, I want an equation. So I start with an equals. And our W here is what's in this cell A2. And I'm going to multiply that times sine. And in a spreadsheet, you need to do the same thing you did in Python. 60 divided by cosine radians 32. And likewise, TAC, and again we want an equation, so we start with equals, and our TAB value is over here in B2, times sine radians 32 minus, again our W value is here in A2 times cosine radians, and let's make sure we do 60 this time. and hit enter. And there's the values in a spreadsheet. Okay. Oops. I hope you enjoy working statics problems with these computer tools. Thank you.